Ever wondered how robots could work together like a well-oiled team, even when the world around them is constantly changing? Today, we're diving into a breakthrough that's making this possible, using big brains and visual helpers to guide robots through complex tasks. Imagine a drone soaring above a cluttered warehouse, while a robot dog scurries below. Together, they need to move a box to a specific spot. But here's the twist. The box isn't in plain sight and the environment is always shifting. How do they figure this out? Traditional robots rely on pre-programmed rules, like a recipe that only works for one dish. But in the real world, things are messy. That's where this new system shines. It uses two key players, a large language model, LLM, which acts like a super smart planner, and a vision language model, VLM, which is like a visual helper that understands images. Here's how it works. The LLM takes a high-level command, like move the box to XXXX, and breaks it into smaller steps. It decides the drone should first map the area, then figure out the best path. Meanwhile, the VLM analyzes the drone's bird's-eye view, spotting objects and their positions. No 3D sensors needed. The magic happens in the collaboration. The drone follows a globally optimized path, sending real-time images to the robot dog. Even if the box disappears from view, the dog uses the drone's perspective as a dynamic compass, staying on track. It's like having a GPS that updates itself based on what the drone sees. This system isn't just smart, it's adaptable. In tests, it handled new objects, confusing layouts, and even tasks it wasn't explicitly trained for. Think of it as a robot team that learns on the fly, adjusting to surprises like a seasoned detective solving a mystery. What makes this research special? It's the first time an aerial ground system has combined LLM reasoning with VLM-powered vision so seamlessly. The result? A framework that bridges abstract planning and real-time perception, enabling robots to tackle tasks that require both high-level strategy and on-the-fly adaptation. But how do robots make split-second decisions in chaotic environments? Let's break down the math behind their common sense. Imagine a robot in a maze. If it gets stuck, it doesn't panic. Instead, it has a zero-point attraction, a built-in, safe zone it always tries to return to. Think of it like a robot's version of when in doubt, go home. But what if there's a chair in the way? That's where obstacle avoidance kicks in. The robot calculates the closest distance to every object around it, like a personal space bubble. If something gets too close, it punishes that path, forcing the robot to reroute. It's like having a tiny GPS that shouts, don't touch that. Then there's the boundary constraint, the robot's no-go zone. If it's near a cliff or a wall, this rule instantly blocks any path that would take it over the edge. Together, these rules act like a robot's survival instincts. But here's the cool part, they're not all equal. Special numbers like QA, Q0, QALOCL, and QW act like volume knobs, adjusting how much weight each rule has. In a tight space, obstacle avoidance might turn up to 11, while in an open field, the robot prioritizes speed. It's like a dance of priorities, constantly adapting to the situation. Now let's zoom out. Researchers are pushing this even further. Take DINOV 2, a 2024 study that teaches AI to see without needing labeled data. Imagine teaching a kid to identify animals by showing them pictures, but without saying, this is a cat. DINOV 2 does exactly that, letting AI spot patterns on its own. This means robots could recognize a cluttered room or a dimly lit street without being told what to look for, crucial for self-driving cars or medical scans. Then there's cooperative navigation between drones and robots. Picture a drone delivering a package to a robot on the ground. How do they coordinate? A 2024 paper shows drones using sensors to locate robots in real time, like a perfectly timed dance. This technology could revolutionize search and rescue missions, where aerial and ground units must work in tandem to navigate disaster zones. The future of robotics isn't just about individual machines. It's about creating intelligent systems that can collaborate, adapt, and solve problems in ways we're only beginning to understand. Whether it's a drone guiding a robot through a maze or an AI learning to see, without supervision, these breakthroughs are paving the way for a world where robots aren't just tools. They're partners in exploration, innovation, and survival. So next time you see a robot navigating a complex environment, remember, it's not just following rules. It's thinking, learning, and adapting, powered by the same kind of intelligence that drives human curiosity. And as research continues to push these boundaries, the line between science fiction and reality keeps getting blurrier. Stay curious and keep exploring.